Good morning, my dear students. In the previous class, we discussed about the electric field on the equatorial line. In today's class, we will discuss about the torque on an electric dipole in the uniform electric field. So, here, what do you mean by torque? In the first year itself, we studied this term known as torque. So, torque is nothing but what? The force into perpendicular distance. Force into perpendicular distance. It is measured in terms of what? A couple. Two equal unlike parallel forces acting on different lines of points is known as what? Couple, and that is measured in terms of what? Torque. Alright? Let me give an example for the torque. Say that when you open the bottle tap, we will apply the force like this. There is one equal unlike forces. When you open the tap, when we open the screwdriver, we apply the equal unlike parallel forces. And these equal unlike parallel forces acting at a different points of line, we call them as what? Couple. And the couple is measured in terms of what? Torque. And torque is nothing but the force into perpendicular distance. Perpendicular distance. And here we have one more term, that is the uniform electric field. Uniform electric field. What do you mean by uniform electric field? It is the field. Electric field at every point is same. And how it is denoted? Say that there is a field. These are the field lines. And the space between these two or the electric field lines is same. At every point I get the same electric field. At every point in this region I get the same electric field, then I will call it as what? Uniform. So it is a uniform electric field. At each and every point at this region I get the same electric field, then I will call this is what? The uniform electric field. So what happens when the electric dipole is placed in the uniform electric field? That is going to be discussed in this class. Right? So let us see that when the electric dipole is placed in the uniform electric field, we know that electric dipole, it is the system of equal and opposite charge separated by the small distance. Say here, there is a uniform electric field. There is a uniform electric field. And this uniform electric field, in this uniform electric field, I have placed an electric dipole. I will place one electric dipole. Say that there is one electric dipole now. Right? This is the dipole. We will call it as the minus Q and this plus Q. We will name it as A and B. Right? This is the center of the dipole. Right? So the any charge which is present in the electric field experiences an electrostatic force. The force acting on the charge is given by F is equal to Q into E. This is the force acting on the charge. Now there are two charges which are equal and opposite. They are separated by small distance. Here AB is the dipole length, which is nothing but what? 2A. Okay. Then these two charges experiences an electrostatic force. These two charges experiences an electrostatic force Now this positive charge experiences the force. The positive charge experiences the force in the direction of the electric field. In the direction of the electric field. So this is the direction of the force on the positive charge, that is F is equal to Q into E. Right? Similarly, this negative charge is also experiences an electrostatic force in the presence of the uniform electric field. Okay, so this is the negative charge. So the force experienced by the negative charge in the electric field is opposite to the direction of the electric field. So this is the direction of the electric field. This is the direction of the electric field. Then the force is opposite to the direction of the electric field. So that is F is equal to Q into E. Right? These two charges are equal and opposite. When the dipole is placed in the uniform electric field, there is a uniform electric field now, and in the presence of the uniform electric field, I have placed one dipole like this. Now you can see from the figure, the force is acting on these two charges at different points of action, and these forces are equal and opposite, and they are parallel forces. They are parallel forces. Look at, one force is acting in this direction, which is in the direction of the uniform electric field. Another force is acting, which is opposite to the direction of the electric field. These two forces are equal and opposite. They are unlike parallel forces. We call them as. We call them as what? Unlike parallel forces. Right? So this is the dipole which is placed in the uniform electric field. Which is placed in the uniform electric field. So when the dipole is placed in the uniform electric field, the force is acting at these 2 points. Different lines of action. One is force acting opposite to the direction of the electric field. Another one is what? Towards the direction of the electric field. This is the direction of this field. So there are two unlike parallel forces. These two unlike parallel forces acting at different points constitute a couple. Constitute what? Couple. And that couple is measured in terms of what? Torque. Hence, remember one thing, that when an electric dipole is placed in the uniform electric field, net force acting on the dipole is zero. It's a very, very important concept. Because there are equal and opposite charges, and equal and opposite charges placed in the uniform electric field experiences what? Zero force. Because there is one positive charge, there is a negative charge. So net force acting on the dipole in the uniform electric field is zero. Right? So there are two equal unlike parallel forces which are acting at different points of action constitute the couple, and that couple is measured in terms of what? Torque. Right? So when we can say that torque is acting, this torque will tend to rotate the dipole. This torque will tend to rotate the dipole. There is one force, there is another force which is equal and opposite. This force is rotating the dipole like this. This force is rotating the dipole like this. Right? There is one force in this direction, there is another force in this direction. This tends to rotate this dipole like this. They tend to rotate the dipole like this. Look at here. Look at here. Like this. Right. So this torque will tend to rotate the dipole. Right. So that we can measure the torque by saying that torque can be measured with force and perpendicular distance. Right. So I draw the perpendicular distance here. I will draw the perpendicular distance from the dipole itself, and I will name it as a C. Right? Here the theta, which makes an angle with the uniform electric field. This is the dipole moment, and this is also the theta now. Right? So torque can be measured. Torque acting on the dipole is torque tau is equal to magnitude of either force into perpendicular distance So magnitude of either force, there are two forces due to the positive charge and due to the negative charge. We can take any one of the force now. So that is force into perpendicular distance. What is the perpendicular distance? This is BC is the perpendicular distance. So BC is the perpendicular distance. What is force here? That is Q into E. That is Q into E. So from figure we can calculate the BC now, right? So from figure, sin theta is equal to, from figure we can calculate sin theta here, right? From triangle, that is triangle ABC, sin theta is equal to BC divided by AB. BC divided by AB. Therefore, BC is equal to what? AB sin theta. AB sin theta. So I can write BC is equal to what? AB sin theta. Right? So it is Q into E into AB. What is AB? AB is the dipole length. That is what? 2A. So it is 2A sin theta. It is 2A sin theta. So I will write this in this way. That is Q into 2A into E sin theta. Into E sin theta. So we have what? Q into 2A. But Q into 2A is nothing but what? P. That is dipole moment. That is nothing but the dipole moment. So we have what? P into E sin theta. PE sin theta I will write here. That is PE sin theta. So tau is equal to what we will get here? That is PE sin theta. Alright. So this is the expression for the torque. This is the expression for the torque. Tau is equal to PE sin theta, where P is the dipole moment, E is the electric field, theta is the angle between the E and PL. Alright. Then there is a question asked in the examination for 2 marks. When the torque is maximum and minimum in the uniform electric field. Right. So when theta is equal to 90 degree, when theta is equal to 90 degree, torque is maximum. And when theta is equal to 0 degree, tau is minimum. So at theta is equal to 90 degree, sin 90 means it is 1. So we write that is tau is equal to simply P cos E. And if theta is equal to 0, sin 0 is equal to the 0, then tau is minimum. There is one more question is asked in the examination: when the torque is stable and unstable. When the torque is stable and unstable. So for 0 degree, that is tau is equal to stable. The tau is stable, means torque is in stable equilibrium. Torque is in stable equilibrium. For theta is equal to 0 degree, torque is in stable equilibrium. And for theta is equal to theta is equal to 90 degree or 180 degree, it is most unstable. Tau is equal to degree, torque is unstable. Equilibrium. Right? So for 0 degree, tau is stable, and for theta is equal to 180 degree, tau is unstable. You can see here. Right? So this is the torque acting on the dipole. Remember, in the uniform electric field, torque acting on the dipole, we can calculate that is tau is equal to PE sin theta, and net force acting on the dipole is 0. Net force acting on the dipole is 0. If there is a non-uniform electric field, then we can calculate the force on the each charge, that is the dipole. Alright, so this is what the electric torque acting on an electric dipole in the uniform electric field. Okay, then now we will talk about the continuous charge distribution. Continuous charge distribution. In continuous charge distribution, you see that a continuous charge distribution. Continuous charge distribution. In the continuous charge distribution, we say that charge is distributed over the surfaces. Right? Charge is distributed over the surfaces. If it is a plane surface, or it's a circle, or it is maybe a straight line. There are three types of distribution of the charges. Suppose that there is one straight wire. We'll say that first one, that is the linear charge density. Linear charge density. Linear charge density. If there is a straight wire and the charges were distributed along the straight of length L, then we can define the linear charge density by saying that it is the ratio of charge per unit length. Charge per unit length. Charge per unit length. So in the linear charge density, charges are distributed along the straight line. The straight line, and it is denoted by the symbol lambda, which is equal to charge per unit length, that is Q divided by L. Q divided by L. And the SI unit of this linear charge density is coulomb per meter. Coulomb per meter. A set of charge is coulomb and the length is meter. So it is coulomb per meter. And the next one is surface charge density. Surface charge density. Surface charge density say that charges were distributed along the surface. Say that this is the surface. This whole board is a surface now, also plane surface. And the charges, if they are distributed along the length and breadth, charges are distributed along the length and breadth like this. This is the length and this is the breadth. So length into breadth is nothing but the area. So it is the ratio of charge per unit area. Charge per unit area, and the symbol of this, that is sigma, is equal to Q divided by E. Q divided by right? So charges per unit area is nothing but the surface charge density. If the charges are distributed along the length and breadth, we call them as the surface charge density. It is charge per unit area. It may be a small charge, that is dq divided by ds or dq divided by dA. The small surface is small area. The same way dq by dn also you can write. And the third one is, that is the volume charge density. Volume charge density. The third one is what? Volume charge density. Volume charge density. In this case, the charges were distributed along its length, breadth and height, like this. So this is the volume charge density, where the charges were distributed along the length, breadth and height. So we can say that it is the ratio of charge per unit volume. Charge per unit volume. So charge per unit volume is nothing but the volume charge density, and it is given by, that is rho is equal to Q divided by V, and its SI unit is coulomb per meter cube, right? And the surface charge SI is what? Coulomb per meter, right? So this is what the distribution of the charges. There are three types of the distribution of charges. One is linear charge density. It is the ratio of charge per unit length. It is lambda is equal to Q divided by L. Is SI is what? Coulomb per meter. There is one more, surface charge density. It is the ratio of charge per unit area, that is Q sigma is equal to Q divided by A. Its SI is what? Coulomb per meter square. And there is one more, last one, that is volume charge density. It is the ratio of charge per unit volume. It is rho is equal to Q divided by V, and its SI is what? Coulomb per meter cube. And earlier we discussed about the torque on an electric dipole placed in the uniform electric field. When the dipole is placed in the uniform electric field, it will experience no force, means zero force, but it experiences a torque. And the torque is given by the expression tau is equal to Pe sin theta. And today in the next class we will discuss about the Gauss law and its applications.